All right, we're ready for today's lesson. We're going to be reviewing some key concepts and also pulling in some reference table stuff. You should have these notes. Notice there's two sides, so glue them into your notebook. If you haven't glued them in yet, stop this video right now and do that. Let's talk about attractive forces in states of matter. So when we're talking about a solid right here, the particles are very close together. See this? And the particles literally vibrate. Okay. And the attractive forces between the particles are really strong. That's what holds them in that regular geometric pattern. When you get into a liquid like this, particles are able to slide past each other. So the attractive forces are not as great, okay? The particles are still close together, just not as close as in a solid. And then when we get to a gas, the particles are really far apart and the attractive forces are so weak and the movement of the particles is fast and random and all over the place in all directions. Density also ties into states of matter, okay? So in general, this is a general rule, in a solid, the particles are more tightly packed, the highest density, and then in a gas, the particles are the furthest apart, and that will have the lowest density. For a particular substance, the density will be the same at the same temperature, no matter how big the piece is. So you could have a small piece of copper, a large piece of copper, and a gigantic piece of copper, and they would all have the same density at the same temperature. But temperature does have an effect on density. So these are all liquid samples of water right here. One, though, is heated water, one is room temperature water, and one is chilled water. And you could see the density is different. So when you heat up the particles, they get farther apart. So this heated water would have a lower density, whereas this cooled water, the particles are more tightly packed, would have a higher density. So looking at these two, which one would have the higher density? Yeah, this one. Density values for elements are found in table S. Okay. All right, so let's fill out this table, which is a recap of what we just did. So this is in your notes, you should be filling it out. So the particles in a solid, they vibrate, they're close together. Strong attractive forces, and the highest density. In a liquid, the particles slide past each other. They've moderate attractive forces and moderate density. And then for a gas, the particles move fast and are far apart, weak attractive forces, and the lowest density. And as temperature increases, density will decrease, and density values are found in table S. Pause this until you get this all written down. All right, so let's go over what these individual boxes represent, okay? A represents a compound because I have different types of atoms bonded together. Also a molecule because it has two or more particles bonded. B is a mixture, so it's two different samples. I have this and this, so it's a mixture. But each one individually is an element, okay, and a molecule. C is a bunch of atoms of an element, and D are molecules of an element. All right, so let's look at your notes right here. So this first box right here, what does this represent? Well, that shows me atoms of an element, so just an element. What about this box right here? Well, that shows me a compound and a molecule. And what about the last one right here? This one represents an element because I only see one type of atom, but also a molecule because they're bonded, right? Okay, an atom. An atom is the smallest unit of an element. It's neutral, so it has an equal number of protons and electrons. We've talked about the structure of an atom before, okay? The number of protons determines the element. Remember when we did the simulation, when we change the protons, the element changes. The nucleus contains protons and neutrons, and electrons are located outside the nucleus, and they're in shapes called orbitals, okay, in the electron shells. All right, so table O actually does give a lot of information about subatomic particles. So you'll see I see neutron and proton are both right here. Okay, it gives me a symbol. This top number represents mass, so that we haven't gotten to all of this yet, but we will. And the bottom number represents a charge, okay, for everything on this table. Top number represents mass, bottom number represents charge. But this one right here is another word for electron. So a beta particle is an electron. So it might look like electrons are not in this table, but they are. All right, here's the Bohr model. How many protons? Yeah, 6. How many electrons? Yep, 6. Here's a different one. How many valence electrons? Yep, 5. And what element is this one? Yeah, nitrogen. Count the number of protons. All right, so the periodic table gives us a lot of information about elements. So we have the symbol, we have the atomic number, which tells us the number of protons. We have the electron configuration, which tells us a lot. It tells us 2 electrons in the first energy level, 8 in the second, and 2 in the third. It tells us valence electrons, that's the last number. And then this one that we haven't really talked about yet, it tells us the charge when it's an ion. All useful information. The element names are found in table S as well. Okay, so on the periodic table, we just have symbols, but you can get the names by turning the page. All right, here's a summary of what we just talked about, but let's look at those last two things. Beta particle is another term for an electron, and the outer electrons are called valence electrons. Okay, on the next slide, you're going to watch a simulation of what occurs in covalent bonding, and then you're going to watch a simulation of what occurs in ionic bonding. So watch what happens. Did you see what was happening in those two simulations? Atoms are not stable until they have the full outer energy level. And in covalent bonds, atoms will share those electrons to make it happen. In an ionic, they're transferred. And all of that has to do with this, electronegativity, which is how strongly an atom can pull electrons in a bond. If it can pull so strongly that it just yanks it away, ionic. If it can just pull it closer to itself, covalent and specifically polar, okay? So in covalent bonds, you can either be polar or nonpolar. In polar, one element pulls harder. In nonpolar, they're pretty much equal. They're pulling both with the same amount of strength. And in ionic, one pulls super hard, so hard it just literally rips the electron away. That nucleus pulls so hard that it yanks the electron over. You can find electronegativity values on table S. Electronegativity values can help us predict bond type. Well, here's what's important to know. It's literally like a continuum. So it's not like at this line, it becomes polar. At this line, it becomes ionic. So you can see as the electronegativity difference increases, you get more ionic. And as the electronegativity difference decreases, you get more covalent. So roughly around 1.5-ish, between 1.5 and 2.0, that's when really the transition between polar and ionic happens. The closer you are to 0, the more likely it is to be nonpolar, okay? And then polar is going to exist mostly in this gradient, and then ionic is going to be the biggest differences over here, okay? So up here, you can see electronegativity is how strongly an atom pulls electrons in a bond. All right, so on the next slides, you're going to work to complete this chart, okay? I'm going to show you some models. So here's HF. What kind of bond do you think it is? Find the electronegativity difference. Record it in your chart. Here's what it looks like in terms of charge distribution. Look for symmetry. So what kind of molecule do you think this is? Write it in your chart. Let's check and make sure you got it right. So that's what you should have gotten, which means it's going to be classified as polar, although leaning a little bit closer to ionic. But I know that hydrogen and fluorine are both nonmetals. So that's really another hint. And because I see partial charges, it's going to be polar. All right, let's try another one. F2, what kind of bond? Find the electronegativity difference. What type of molecule is it? Look for symmetry in the charge distribution. All right, let's go over it. Is this what you got? That should have been your subtraction, which means obviously nonpolar. And what type of molecule? There's symmetry, so it's nonpolar. All right, let's look at this one. What type of bond? Find the electronegativity difference. What type of molecule? Look for symmetry in the charge distribution. All right, let's see if this is what you got. You should have gotten this difference, which means it's polar. It's not as polar as HF, but it is still polar, okay? And what type of molecule? Well, here, look, if you can see, I have negative right here and negative right here. So negative pulling this way and negative pulling this way. So this molecule has symmetrical charge distribution. So it ends up being nonpolar. All right, and now let's look at this one. 2 bonds to look at between C and H and between C and N. Find those electronegativity differences. Now let's look at the charge distribution. Look for symmetry so we can figure out what kind of molecule it is. All right, so let's see, is this what you got? For carbon and hydrogen, it's nonpolar officially, but it's really leaning a little bit polar. Okay, it's not at that 0 mark, so it's like slightly polar. And it's going to be the same for CN, so slightly polar. Okay, so this molecule then ends up being polar because although the bonds tend to be more nonpolar, there is a slight pull because you can literally see the charge distribution. Okay. Now, on the next slides, we're going to watch the molecule behavior and see what happens when we change the electronegativity value of elements and how that behaves in an electrical field. Did you see how those molecules behaved? How just moving the electronegativity values really changed like how much partial charge there was and how the molecule responded to the electrical field. Did you notice which part of the molecule was attracted to the negative electric field and which part was attracted to the positive? Doesn't that make sense? All right, remember that water sticks to itself like super well. In fact, we're going to give it a name. Uh, it is called a hydrogen bond. That bond between hydrogen and oxygen of neighboring water molecules is so strong, and it's called the hydrogen bond. All right, look at this. Salts have charges. Polar molecules, like water, have partial charges. And this helps to explain how salts dissolve in water. But you see how even water has to kind of pull hard, and stirring helps move the water molecules, which actually assists in the dissolving in water's ability to pull those ions apart. Okay, so water sticks to itself. Salts are ionic, and salts dissolve in water. So here's an example. Aluminum sulfide dissolves in water. Add the two ions, symbol and charge from the salt, to the diagram below. So we have aluminum and we have sulfur, which is sulfide in a compound. So what's going to happen is this is going to, electron is going to go here. This one is going to go here. But now we need another sulfur, so this one will go here. But now we need another aluminum, so this one will go here. And now we need another sulfur. This one will go here. Aha, this one will go here. Whew, finally. So we have aluminums with +3 charges, sulfurs with -2 charges, but we have 3 aluminums and 2 sulfurs. That's just a reminder about how we get compounds, okay? So what ions are involved? Well, we have aluminum and with a +3 and sulfide with a -2. If you remember, oxygen, right, in water has a partial negative. So if the negative part of water is attracted here, that means this one must be what? Positive. And if the positive, partial positives of water are attracted here, that must be the negative. So those ions are going to go in like that. All right, in the next ones, I just want you to look at electrolytes and showing how some things conduct electricity when they dissolve in water. All right, so did you see how the salt conducted electricity, but only while it was dissolved in water? As soon as we evaporated all the water away, it didn't conduct electricity anymore. So things only conduct electricity when they have charges that can move. And when the salt is a solid, the charges can't move. Okay. And then non-electrolytes like sugar, we can add it to water, but it doesn't make it conduct electricity. Whew, okay, that was a lot. A big recap. I hope this helps.